Welcome to episode 2 of Roundtable Ruckus. Today we're here to talk to you about all things drivetrain and drivetrain selection. So we've got co-hosting with me, we've got Kevin here. Kevin, can you give a little bit of your backstory and kind of what you do here at AndyMark?
Hey everybody, my name's Kevin Kaloje. I'm the mechanical engineering manager here at AndyMark, and I've been involved with FIRST for 20 years now, mostly on the FRC side and Lego side, but you know, getting my feet wet with FTC here, and a lot of lessons learned there will apply as well. So, yeah, happy to be here.
Cool. Thanks for joining us. As always, I'm Danny. Behind the camera today, we got Ruth and Brett helping us out on the technical side. But we're gonna dive right in. This year, there's some interesting drivetrain challenges on the Rover Ruckus game field, and that kind of really all comes down to the craters. We got some crater sections here out in front of us. And there's a lot to understand about this game, and a lot of different ways that your drivetrain can play into account. So, you know, some of the things we're going to try to touch on today, you know, trying to pick out some wheel sizes, trying to look at some powertrain, maybe some gear ratio kind of different stuff. Look at some drivetrain archetype, you know, sort of overall between Mecanum and tank drive and tank treads, you know, and some of the different things that are out there. You know, but Kevin, you've been in this game for 20 years. You've been building robots, you know, all sorts of different robots. What are some of the key things to kind of keep in mind, you know, and when you see the craters, you know, on the game field, what are you kind of first looking towards at how you're going to overcome and get over that obstacle?
Well, sure. So, you know, one thing that I've definitely learned over the years and taught to my teams that I've been involved with and my students is, you know, the importance of your drivetrain. You know, and no matter what the game is, no matter what the rest of the challenge is, in most cases, if you can't move, the rest of the game won't matter. There, of course, have always been a few exceptions throughout the years of some robots that didn't have drivetrains and could be static. But you know, in a game like this, where you have game pieces that are behind an obstacle and you have to do cycles, essentially, if you're going to score a lot, you're basically running cycles because you can only hold so many game objects, that you need to be able to get there and get back. So, you know, the importance of your drivetrain cannot be overstated. That should be your number one focus. Once you're done with your drivetrain, you should continue to focus on your drivetrain, and that should be your number 2 focus. That's how important your drivetrain is. Because if everything else fails on the field, and you can still drive, you can still move objects, you can still park, you can still get to where you need to be. You can continue to score points even if nothing else works, if you can still drive.
I think that is some fabulous insight. I think that's some really great, you know, takeaways there. Before we went live, you're also talking about, you said goal number 3, still related to drivetrain. What would priority number 3 be?
Yeah, so you can have a great drivetrain, but you still have to be able to drive it. So number 3 on my list is learn how to drive your drivetrain. It's never too early to start practicing your routines. Like when I've been a drive coach for a dozen years or so at least, and one thing that I always instill into my drivers and my students is practicing their routes, like the importance of where you're going to be, when you're going to be, and then, you know, you of course have to coordinate that with your partners at the competition, but you need to understand how you're going to do. What is your entry angle? How are you going to attack? Especially with this crater, it's got that nice arc. I think we've got a diagram of the crater here. So you've got that arc that you're coming at it. Do you want to attack it perpendicular? Do you want to come at it at an angle? So these are things that you're going to have to find out what works best for you and your robot, and how you're comfortable if you're going to be driving over the crater. So that practice is extremely important.
Yeah, and I think there's, you know, with 2 of the crater sections are flipped around backwards. So if your drivetrain tends to work better, you know, going up the shallow side or the steep side, you know, knowing those things, knowing how you're going to get into the crater, but also how you're going to get back out of the crater, those things are all super important. One of the things that I've done when drive coaching teams is, you know, we sort of have this plan of, you know, we have sort of the tasks that are sort of the unless otherwise directed tasks of, like, plan A is always go from here to there, from scoring game objects on the lander back to the crater to this crater, not the other crater, but this is our plan A crater, and we're just going to keep doing that. If something happens, that's the sort of default plan, but then knowing those backups, knowing those, you know, alternatives,
right,
being able to call that audible.
I was going to say the exact same thing.
So I think that kind of plays into a little bit. one of the key factors in sort of selecting drivetrain and sort of playing with different drivetrain, oftentimes there's a lot of gear ratio, and that ties into wheel size. You have to those two go really closely together to kind of get a target speed for the robot. Now we know in First Tech Challenge, kind of by far the be-all and end-all, the default go-to drive motors, the Neverest 40. And that, coupled with a 4-inch wheel, gets you to about 2 feet per second, 1 tile per second across the game field, which is a pretty, it's a nice, driving speed. You can definitely go a lot more driving mistakes. You can go a lot slower. And we've seen some people do that, especially with, we saw a little bit of that in Relic Recovery, people gearing down just to be able to sort of push the pile and do that kind of stuff. But there's also been a bit of a trend in the last couple of years with the new Neverest 20 orbitals and some of those things and slightly bigger wheels to start gearing for speed and start going a little bit faster. So you had a really nice knowledge nugget about kind of how to select some of that.
Yeah. So I encourage teams to find what they're comfortable with, and then just go a little bit further. Like push that envelope, because if you stay in a safe zone, most teams are going to stay in your safe zone in terms of what they're comfortable with their build. So sometimes you need to make that slight little difference will be the difference maker out on the field. So if you're going to be on par with everybody and you can eke out that one extra cycle, that could be the difference in your match. So don't be afraid to push those boundaries, especially while you're in development mode, and practice that. But don't be afraid to also say that it's too much and come back to what you're comfortable with. That's totally okay. Nobody's going to fault you for trying something. That's why we're all here. So
run the experiment.
Yeah.
Absolutely. So I think one of the really cool things is that sort of come about with Tile Runner, with the Pico boxes, with some of the other stuff that's out there. Robots, drivetrains are not just limited towards sort of the big major steps between Neverest 60 to 40 to 20. On percentage-wise, those are huge, massive steps between one thing and another. One of the things that we can do in sort of the Pico box phase of the drivetrain is we can make a lot smaller step. It's about a 30% jump as opposed to something more akin to a 100% jump. So we can work through that to sort of help dial it in. If we think an Everest 40s, or if we think a 40 to 1 gear ratio is right, maybe we go a little bit to the high end. We can play with it. If that's not right, we can always just swap gearing around, go back to that 1-to-1 kind of gearing. So I think that's a great kind of tidbit, great piece of information. So one of the other things that we've learned about FTC kind of chassis and more of the structural point is it almost seems like you can never go too rigid with your chassis. You can never really get too strong. But this year we have a big weight penalty, and a weight consideration. So there you got to play that balance of strength versus weight. Are there any things that you can kind of point to, from games gone past, maybe some of the old games, some of the effects that flexi chassis have sort of played?
Yeah, no, certainly I've had my fair share of not quite square chassis or imbalanced chassis that make turning really difficult, make you kind of rock and tippy as you're going. In some cases, it's not a bad thing. Like in a Mecanum-based chassis, you want to have a little bit of flexibility because you want to really make sure that you're getting that contact on all four corners. But there's a difference between flexibility and cattywampus chassis. You don't want to have it where two wheels are up in the air the whole time. That's a different problem. That's not so much flexibility as it's just things are being pulled or pushed in a certain way. So, but yeah, I've found through the years, the more rigid our chassis have gotten, the better our performance has been, because it makes sure that your gears are going to stay in alignment. It makes sure that your bearings are running properly. You've got all these advantages that you want to make sure that you have that good solid base. And if things are going to go wrong there, it's going to ruin the rest of your game.
Yeah. And the chassis really does set sort of the foundation for the whole rest of the robot above it. So if you start with a good, strong chassis here, kind of the stuff above it, gets better. One of the
and that's something to think about too, especially in a game like this where you might having to be reaching out with something to pick up the game pieces or reaching up. That depending on how you have those other elements of your robot anchored to your chassis, you might think you have a solid rigid chassis to start with, but then as you start shifting weight around, you might start seeing different areas or different components start to flex that you hadn't thought of. So be aware of that, and again, there's the weight penalty this year, so you have to be careful with that, but you might be able to get creative with how you brace certain things, and maybe you have to experiment with some tensile members to keep things rigid instead of just strapping on another piece of metal.
One of the other big things that we've seen, and this is some feedback that we've gotten from teams out there, is the stronger your chassis is, the more rigid your chassis is, actually has a symbiotic relationship with how accurate your autonomous mode is. Now, drivers that just kind of drive to get the robot at a spot, so they can take into account and kind of adapt and account for a lot of different discrepancies. But your autonomous mode, it just does what it's told. And if a different amount of energy goes into flexing the chassis each time you try to like make a turn or do something, then where that turn or where that drive is going to end up is in question. There's a lot of variability to that. So by reinforcing and strengthening the chassis, it actually goes through and makes a lot of the autonomous programming a lot more accurate. So I know, tongue-in-cheek, a lot of times mechanical team and software team, have it at odds with one another. But this is one of the spots where both goals are aligned and in the same direction.
Yeah, I can't stress that point enough. I've seen so many robots that will veer to one side or another during autonomous when the driver subconsciously is correcting for that.
Right,
you say, well, it doesn't happen when I'm driving. It only happens during autonomous. Well, it does. You just have practiced it out. So that is definitely something to be aware of. And eventually maybe you can compensate for it in the way you program that routine. But then let's say you change a wheel and now it behaves completely differently. I know I had that problem at championships a couple years ago where I had it set. I knew exactly how I had to align the robot to get autonomous. Then we changed our wheels, and we never hit another one. So,
so cool. So I think let's dive in a little bit. Let's talk kind of about the crater here for a little bit. Now, for anybody who's still looking to who's ordered game pieces, who maybe hasn't received those yet. We can talk a little bit about the crater as you're sort of sketching out sort of drivetrain, or you're looking at different things. There are CAD models for the crater section and the crater as a whole up on the AndyMark website. We have, like Kevin showed, we have the prints, we have the drawings, so you can pull dimensions from those things. So here we have the crater section drawing, and you can pull a lot of really good dimensions off of those. If you can expand these parts, or if you can expand these drawings, they have the scale down at the bottom. So this is a 1:4 scale drawing. So if you just go and you enlarge the drawing, 4x, then you can get a 1-to-1 print. Maybe you could cut the shape out of cardboard. You could do some different things to kind of get a sense of a real world scope of what the crater might look like.
Oh, I love cardboard prototyping.
That we kind of joke, but CAD, cardboard aided design, is a really powerful tool. It's a really great way to do things sort of full scale in the flesh, right there in front of you. I know a number of the teams that I've worked with, we've done it in cardboard first, got sort of the rough shape, brought it into the CAD model, refined everything, and then took it to the workshop. And then at tournaments, you skip the computer part, you go right from cardboard to real life. But if you don't have a crater, then some of the things that they're a little bit hard to come across in a CAD model or whatever is, one of the things is the texture of the crater section here. So it's not the sort of a perfectly smooth like we've seen in a lot of other plastic components that we've had in the past.
Like the game pieces.
Yeah, exactly, game pieces, like buckets or the beacon housings or some of those things. So we worked with manufacturers, we worked with game design committee to try to figure out what the right amount of texture on these are, and we wanted to give them a little bit of texture, help robots climb over them. Thought that was something that was important. And also a perfectly smooth surface would not look like a crater on space rock. So help the look of the field a little bit better too. Yeah, so some different things, to kind of take into account. This profile here, it's not just a straight ramp anymore. We've had ramps, for a number of years in FTC. We've got a little bit of a lip, something to kind of, keep in mind. Now, almost any size wheel will be able to kind of cross this first, threshold.
Yeah.
I think it's about 1/4 of an inch. And then, kind of driving up, you want to make sure that we don't. One of the issues that we actually had on one of our test chassis, just over my shoulder here, some of the bolts in the chassis were hanging down below the robot and were scraping on the crater rim here and not getting us up and over. So even some simple stuff of having all the bolts pointed the right way and kind of having a smooth bottom to the robot can be a big impact in getting up and over this crater.
Yeah, it's interesting that on a shape like this, it doesn't necessarily come down to ground clearance. Like, you can still have a fairly low ground clearance, but there are things you can do, like Danny mentioned, with you flipping around bolts so that you have smooth surfaces on the bottom. I've had similar challenges in the past where we've put skid plates on the bottom of the robot and just put like a piece of plastic on the bottom of the chassis to give it an edge to actually slide as you're going over. So you're still maintaining traction and you're able to slide over rather than necessarily like pull yourself over or have a void in your chassis to accommodate that ridge.
So I think that's a great kind of segue, great transition. There's sort of two major schools of thought for how to cross a barrier such as this. There's to use a little bit of kind of automotive world. There you can rock crawl your way over it, kind of slow, methodical, big wheels, high ground clearance, lots of torque, go at it slow, and just sort of drive up, drive over, and have the power behind the robot to go do that. You can do it at any speed, at any angle, whatever. The second school of thought would be, to kind of go like a Baja truck, get a good head of steam, get flying, go full Dukes of Hazzard, and hit the jump and use the momentum of the robot more than sort of the torque or the grip, and almost jump the crater. We've played around with a little bit, and we've seen some video of some people doing out there. Any insight or any prior experience that we might be able to pull on here? Any other similar games?
Well, on the FRC side, there was a game a couple of years ago, Stronghold, that involved lots of different obstacles that had to be traversed. Some of them were, a 4-inch tall bar. Some of them were different heights. The rough terrain was one. Some of them were larger, or small. A couple of smaller bars with space. The moat had that. So there were a lot of different approaches taken in that game by different teams. Some of them would, like you said, Dukes of Hazzard and just kind of fly over. I know our robot got airborne a few times, but a lot of them, the kind of the really interesting ones to watch. Well, not that wasn't interesting, but I think of the Mars rovers and all the suspension that's going on in the linkages and the drivetrain there. That you like you said, the rock crawler, that you just kind of your robot is very steady as it's going over, and you're not going to risk tipping over or tumbling over like you did a few times. But there's those different approaches. Yeah, absolutely. So there's history, or there are examples out there to reference that you can take a look at. So again, that's the Stronghold game from 2016 on the FRC side.
There's a ton of great information. Website, thebluealliance.com, has all of the match footage archived, so they can be a really great resource. We never sort of start a project without going back and looking at prior examples. And one of the points you brought up, the suspension, but also not exclusively looking at how your wheels go up and down with respect to the chassis, but also how your electronics, your components, the interior of the robot is sort of mounted in. We've got on these robots, we've got a phone, we've got the rev controller, we've got battery, we've got different things that we want to keep maybe isolated from that shock.
Right.
I know for the Stronghold game, the team I was on, we actually put our electronics board on its own shock absorbers, so that
great
way
idea.
the robot would fly over stuff, and then that would help deaden out a lot of the bounce. So for if any of the FTC teams are looking at going over this thing with a bit of speed, definitely be thinking about how do we protect the phone, how do we protect the different electronics, make sure everything stays where it's supposed to be.
Yep. And there's ways you can do that within the wheel set too. For instance, I don't know if we want to get into that robot behind you yet, but this robot was an experiment of what happens if you put compliant wheels as the drivetrain. So instead of your typical the 4-inch stealth wheel, this one has the compliant wheels on it, the 60 Shore durometer black compliant wheels that have some give to them. So they'll act like a traditional car tire that is air filled, except these are they're just compliant rubber. So so we did some experiments with this going up and over the crater, and even in your initial test, one of your ideas was thinking related to the drivetrain, but another part of the challenge was your starting configuration.
Yes.
So I don't know if you want to talk about that a little bit.
We, on last week's episode of Roundtable Ruckus, we were talking about starting from the lander, starting latch at the top, and then just doing a straight let go, and falling 4 to 6 inches, wherever the robot may grab it, and using the compliant wheels there as a shock absorption sort of feature, landing on the soft tiles to help protect all of this stuff and soften the impact on the robot. And then we were driving, that worked out, really nicely with, these particular wheels. We were driving the robot around, and we were intrigued about whether or not we were going to see a hit in drivetrain performance because we had sort of this non-standard wheel, because we didn't have a stealth wheel. Thought maybe we'd get a bunch of flex back and forth, in the wheel that would make it drive, no good.
Rolling over, digging into the edges, that sort of thing.
Catch an edge. And we were a little surprised. We were really excited that these wheels still drove really, really nicely. Now we know there's a limit to this. We've in some much previous experiments and whatever, we've had something as silly as the green wheels on here. I mean, those are like stress ball squishy, and we had them on as a drive wheel, and they did all of those things to a cartoonish level. They folded over, they rounded over. The robot sat much lower, and so there's definitely a limit. You can definitely go too soft on those wheels, and so that would be something to kind of keep in mind. The black sort of medium to high, stiffness. Wheel, seems to have, worked out really well so far. And it let us, kind of Dukes of Hazzard jump our way over the crater, and we didn't really see a lot of things. Now there were, 2 things that we sort of learned about. One, it may mean that you land on top of game pieces and not in front of them.
Yep.
So that could have a big impact in how your game piece collection happens. You don't necessarily need to just be here, sort of on level with the robot. You may also need to go down below the robot.
It's also a concern that in a configuration like this with your belly pan like that you could actually, beat yourself on top of the game pieces. So that is something to be aware of.
Yeah, the Dukes of Hazzard approach is a little bit, it's going to catch more attention. It's more energetic, more exciting, but it is riskier. It may be a faster way to get in and out of the crater, maybe a faster way to do those cycles, but there's a risk reward there, and that's sort of very typical of everything in engineering, is that there's risk reward tied to everything.
So that's one approach to the problem of getting up and over into the crater. There are some other approaches. This one behind us here, we talked about ground clearance. Now, I understand that these wheels are not legal. do not build this robot as you see it. But this is an example of a really high ground clearance robot that has this void in the middle here. So actually, if you could bring that crater back, you can imagine how you're going to go up and over. Now you're at the point where you can actually straddle the crater. So this might be something advantageous to you if you're thinking about how are you going to get into the crater and pick up those game pieces without getting too far in. So this, this might be something down the road that you want to go with. Now this is built with the Tetrix, the frame system from the Tetrix robots, which is a little bit different construction style than what you see on these others with the tile runner. But it all comes down to the choices that you want to make with your team.
Yeah. This was something that we kind of put together. We were looking at testing and evaluating the crater with the crew at first and with the game design committee, and kind of running some experiments back and forth with them. So we were looking, using parts that kind of any rookie team or anybody might have in their things they get from the storefront, the FTC storefront. Using the Tetrix components and sort of the stock motors and gearing and a lot of that kind of stuff. We put these wheels on there to sort of give the robot a little. We refer to that as artificial normal force. By upping the coefficient of friction, quite a bit. We also tested with weight, different total robot weight and some different things. We did a little bit of experimentation and found that this worked pretty well. And so that was something that like Kevin said, pretty much anybody kind of has these parts and can kind of go make this style of a solution. It's only a 2-motor drive, so it is definitely more that rock crawler kind of scenario. But you can drive into the crater, you can spin around, you can drive back out, you can kind of do whatever you need to do.
Yeah, one really good advantage of a design like this has to do with your center of gravity. If you think about, you're going to have some sort of a structure. Like if you look at this robot, there's a structure on it. You might have an arm or an elevator or something in there for your end game, for your drop off the lander in the beginning, and certainly for scoring game objects. If you've got all that on that robot, you have to think about the angles that you're going to be at when you're going through your crater. On a design like this, you can imagine as you come up and over, that's pretty much your max angle that you're going to see right there. That's not very much at all. But if you imagine there's another wheel in the middle here, when you get to this point, now you're going to be rocked back at that point or this way, depending on which way you're balanced. That starts to get into the danger zone a little bit of if you've got your mass up here, you're going to go up and now you're going to be on your back. So think about that as well when you're choosing your drivetrain and how you're going to approach the crater.
Yeah. I think we can sort of take that segue. We were looking at kind of evaluating these robots, and we were playing with the center of gravity at different spots, and we were playing at sort of total weight of the robot. So the tile runner chassis, we know weight's kind of the big thing here. The tile runner chassis, depending on the configuration, be them stock or tread runner, Mecanum wheel, they range kind of anywhere from 11 to 13 pounds, about a quarter of sort of the total robot weight. And one of the things that we can, so then we looked at the robot with like a 25-pound, barbell weight, kind of just above the chassis. We wanted to see what would happen when we threw extra weight at it, make sure that we kind of test more of a full robot, less just the drive base. And for a lot of these, that worked really, really nicely. Drove right up and over, no problem. When we went to, and we'll cut to the video, when we took our 6-wheel drive tile runner and we put that same 25-pound weight all the way at the very top, that moved our center of gravity up about a foot off the ground. And it hit it kind of went like this. It hit the front side here and just went clean over and actually onto its lid. And so, that's a big consideration. And that actually happened almost more so on the momentum of hitting it, not even any like actual full angle that the robot was on top of the crater. It just sort of hit and flipped over. So be conscious. Yes, there's a weight limit this year, but there's also some significance about where your center of gravity is, and really trying to work to keep that low on the robot as a whole. So there's a number of cool videos that are coming out on Reddit and social media. You know, teams that are sort of showing off their drive bases. We've got a lot of the robot in a weekend, robot in 30 hours. A lot of different teams doing their sort of quick builds. So there's already a lot of different examples out there from the community of teams getting up and over these craters. One shout out that we like to kind of give in particular. It hit the FTC subreddit, and they have a video on their Twitter. But Team 6287 Vertigo out of Illinois, they've got a really cool video. It's a 4-wheel drive robot with 6-inch wheels, sort of a really old AndyMark product, an original. I believe they only have the title of first wheel, but it's sort of a 6-inch smooth tread wheel, sort of the great-grandfather, big brother to the stealth wheel. Similar, same tread material, but they've kind of gone for the high ground clearance, sort of thing. They've got a really cool video. The robot just kind of cleanly going up and over the crater. So good work, 6287. Really cool robot. So keep up the good work to those cats over in Illinois. But I think now we want to try to spend some time. Andy teased it in the AM and the PM show last week, Thursday. But I think we want to spend some time talking about, I guess, the elephant in the room. the centerpiece on our table here. This is our tread runner, tile runner configuration. You can see here we have sort of the stock standard tile runner plates, crossbars. The electronics package that we have on here is sort of our zip tied on quick prototyping thing, so we can just get something off and running as fast as possible. We use our cheap and dirty control system, and we don't have to program phones. We don't have to we just plug things in and we get go. So that helps us prototype here really quickly. But the treads here, there's some special stuff here about the treads, a bit of legacy design. Back in the 2016 game for FRC Stronghold, we had the really rough terrains that Kevin was talking about, and so AndyMark had sort of had coming through development for a while a tread system, and so we actually used the same sort of interior belt geometry. We use the same cogs or pulleys as the Rhino track, except now we have a much shorter belt. We have a new tread surface, so something that's optimized around soft tiles and not tight pile carpeting. But we were able to carry over a lot of those lessons. So we know that we want the drive sort of on the rearmost cog, and one of the reasons for that is belts work in tension, and so now the tension component of the belt is the part running across the ground coming through the drive, and then we can be a little bit looser, a little bit more flexible up across the top as it wraps around this pulley and now gets dragged kind of over the floor. We're still running a center cog, and that's in the same holes as our normal 6-wheel drive center wheel would be in. So we still have that drop center drive. Robot driving performance is still really good. And then one of the other things that we sort of pulled from our Rhino development is the need for a belt tension system. And so we have, that's what this little system is here. We get extra wrap around our drive cog, but just a set of bearings on another churro, so that way we can get good wrap. We have a little bit of adjustment. This system here doesn't require any modification to the rest of the parts. But there could be some adjustment here. If you wanted a little bit less tension, a little bit more tension, you can kind of move that around in some more digital, discrete locations, not quite the analog system that we had on the old robot. But I think one of the final things, I'll just give this a quick spin. In order to facilitate drive at the rear end of the robot, one of the things that we had to do, and the Tile Runner gives us this capability, is we can actually mount our PicoBox Duo at the rear end of the robot. Now this does only work when you're running the classic motors, so our classic 40, our classic 60, because we need the ability to run the motors sort of in the front and the middle spots on the gearbox, and then have the output shaft on the rear section of the gearbox. But now this output shaft goes in direct drives our farthest back pulley cog. And then we just use the belt to drive the other 2 cogs, and so we sort of have our idlers, up at the front to give us, the good drivetrain performance. And we can still play with, even in this configuration, like you see here, we can still play with the gear ratio out to the drive cog. So in this one, we geared up for speed. So we have a little bit of an overdrive here, and the total gear ratio is about 28-1. So kind of in between, where we, the different ends that we can go. And that kind of gives us the ability to kind of really sort of fine-tune the robot's drive characteristic. Kind of like Kevin was saying earlier, find what you're comfortable with and try to go, that one step further. The Never S40s on 1-to-1 gearing, they drove well, but we wanted to see what, a little bit faster would look like, and the robot drove well there too. Speeding it up a little just gives us, that many more opportunities to make cycles, throughout the course of the match.
So one of the advantages that you get from using this tread rather than 6 wheels or 4 wheels is, like we talked about earlier, is what happens on the bottom of your chassis as you're trying to go over a crater. So it's kind of a double-edged sword here. You don't have any place where you can get caught because you have a constant surface on the bottom that is driving, but at the same time, that's also going to make it easier for you to pop up to a higher angle because of how you're going to be driving. So do be careful with that and think about maybe you don't need to go in all the way into the crater. There are those options too. Or you just need to design for that. If your robot is fairly compact, that angle probably won't matter. So there's nothing wrong with that. You just need to consider it.
And I think we can kind of end on that concept. Looking at our Mecanum tower in here with both the new HD and the old SD wheels. A robot like this may not be very well suited for going in and out of the crater back and forth. There's lots of place to kind of get hung up, and the Mecanum wheels, they provide a good bit of traction, but given the configuration, the rollers and whatever, there is some drivetrain losses there, and so a robot with Mecanum wheels, maybe for that perfect lineup, on the lander later. Maybe a robot like this doesn't go into the crater. Maybe it parks at the edge and extends an arm out, over that way. So your drivetrain does not necessarily have to go in and out over the crater, but that definitely should be something that you kind of take into account with kind of the holistic robot strategy. So that's our show for this week. Thanks for joining us here on Roundtable Ruckus. We hope that you'll be back next week for our episode on game piece collection and sort of designing around weight and taking those things into account. We've talked about a lot of different things here. A lot of different things come into account when sort of designing your drivetrain. So we hope that this has been a great resource, that you can take some of the concepts and the things that we've discussed here and sort of springboard from there and kind of take those even farther. And we are excited to see what all the FTC teams come up with for this season playing Rover Ruckus. So for my co-host Kevin, for myself, for Ruth and Brett, and the whole team here at AndyMark, we wish you good luck this season and have fun with Rover Ruckus.